it's really a pleasure to introduce Maurice Herlihy to the audience. First, Maurice, thank you again for agreeing on giving a talk in this seminar. It's really a pleasure to have you here. And it's a pleasure because it's undeniably Maurice is one of the top leaders, world top leaders in this field of computing. So it's really an honor to have you here. And let me say a few words about you before you start your talk, so that people know a little bit about your past. So Maurice studied mathematics first in Harvard, and then a PhD in computer science at the MIT. And then he has been working as a professor in Brown University for quite a long time. And he has been recognized many, many times. He's recipient of the Dijkstra Prize 2 times, in 2003 and 2012. Yeah. And also he was recipient of the Gödel Prize in 2004. And in 2008, he was awarded with the ISCA Influential Paper Award, and many others awards, prizes, and recognitions. So it's really a pleasure to have you here and repeating this. And today, Maurice is going to talk about failure is literally an option. Atomic commitment versus optionality in decentralized finances. So please, Maurice, and yeah, go ahead.
Let me I'm trying to share my screen here. There we go. So Armando, thank you for that introduction, and thank you for inviting me. This is
Maurice, you are showing us your controls.
Yeah. Yeah, we're looking at.
Perhaps you can start the screen share again and select the second desktop. That's the same I did with the coffee break. So.
Okay.
Perhaps this is it because you have 2 monitors. Yep.
Yeah,
Yes,
controls.
Yeah, again.
Again, try again.
Controls out there. Is it PowerPoint?
This is PowerPoint, yes.
Okay. There is one control to disable the controls in PowerPoint. Let me check.
I can try sharing the.
Do you have? Sorry. Do you have 2 screens, Maurice?
Yes, I have 2 screens.
Oh, that must be the problem. If you can disconnect the second one. Oh, that's great.
Oh, now it looks better. Yeah.
Yeah.
Okay, so that's the.
Now try to start the presentation. Let's see if it is working fine. There it is.
Yeah.
Okay.
That's fine. Perfectly.
Okay, thank you. So the this is me. This is joint work with my 2 students, Daniel Engel and Yingjie Shui. This is work that will appear in a conference soon. So the basic premise is that in the future, there will be many different blockchains. It's not realistic to think that everything will be run in a single central blockchain because there will be different administrative boundaries, different technologies, different governments, different regulations. But a blockchain is valuable only to the extent that it can communicate with other blockchains. If your blockchain that manages your currency or your mangoes or your real estate will be helpful only if it can communicate with blockchains that manage money, for example. So the ability to coordinate value transfers across blockchains is often called, it's a form of decentralized finance, which is called DeFi in most of the literature. Now, what I want to do in this talk is I'm going to trace the roots of a single idea from its origins in classical distributed computing to its modern form in decentralized finance. And the reason I'm doing this is largely to demystify blockchain and decentralized finance. It's often the case that the blockchain world reinvents ideas that were invented in distributed computing, gives them a different name, and it often adds new and interesting aspects to these problems. But what I want to emphasize here is that one way to approach understanding these ideas is to trace how they developed. I'm going to start with an analogy. So the people who invented airplanes were originally bicycle mechanics. So the Wright brothers, for example, had a bicycle shop. They were good at building bicycles. And in fact, the first airplanes looked like bicycles. If you look at the frame on this airplane, it looks like a bicycle frame. And the engineering that went into them was basically bicycle engineering. Now, as the technology got more mature, the airplanes looked less and less like bicycles, even though the evolution, the genealogy is clear. It's hard to tell by looking at this plane that its ancestor was a bicycle. And today, modern planes look very little like bicycles. And yet, the jump from each picture to the next is something where you can see that one is linked to the other. So what I'm going to do here is to trace an idea from distributed computing, into decentralized finance, and into more and more specialized financial instruments. And what I want to claim is that the DNA behind these ideas is very much the same. And that if you understand the way that these ideas developed, it's much easier to understand, where they are going and how they are built. So I'm going to explain why all these ideas, while they may look superficially very different, are in the core very much the same thing. So I'm going to start with something called two-phase commit. So imagine here we are in the late 20th century, long before blockchains were invented, before the word was coined. And we have two characters, Alice and Bob, and they make an agreement that Alice will give $1 to Bob at a New York bank, and Bob will give €1 to Alice at a Paris bank. And so these, the New York bank and the Paris bank are obviously far apart. This isn't a blockchain world. This is a distributed database world. And this has the property that, say, the software on both banks is run by the same company, so there are no trust issues. So in New York, Alice wants to give the $1 to Bob. In Paris, Bob wants to give the euro to Alice. But naturally, you have to make sure that both of these transfers happen, or none, or neither transfer happens. So we want to guarantee atomicity here. Now, the classical adversary in this kind of distributed systems are basically operational failures of hardware. So nodes can crash, networks can lose messages, network switches can become overwhelmed and messages can be delayed and reordered. So when we design a fault-tolerant algorithm, we can think of ourselves as trying to outwit an adversary that can cause hardware failures. Notice that we trust all of the participants to follow their roles. So the adversary can do crashes, it can play games with timing, it can omit messages. So the database technology, basically there's a stable state which doesn't go away. And the committed stable state is in some sense the permanent state of the database. So in New York, we have a record that says that Alice owns $1, and in Paris, it says that Bob owns €1. Now, when we make these changes, we make them tentatively, speculatively. So we make a tentative change saying, okay, let's set Alice's dollar balance to 0 and Bob's balance to 1, and vice versa on the other database. Now we have to make sure that either both of these changes happen permanently or neither one does. So we appoint a trusted centralized controller. This was easier then because both databases were built by Oracle or someone like that. So we're not worried about betrayal of trust. And the centralized controller in phase 1 of the protocol says, okay, both of you prepare to commit. And both databases write their tentative changes to stable storage. So at this point, if a crash happens, the tentative changes will not be lost. Then each database responds saying, yes, I vote to commit, or no, something happened, never mind. And then the centralized controller says, well, if everybody voted to commit, then commit. And what does it mean to commit? Commit says, I'm going to replace the old value with the new value, the old state with the new state. And now we have successfully ensured that both the dollar and the euro have been transferred at separate, independently failing databases. This is one of the oldest techniques in the distributed database literature. Now, if something goes wrong, if there's a crash or something, then the protocol will restore the database to its previous state. If somebody votes not to commit, then the controller will say, okay, never mind, abort the transaction, throw out all of our changes. So this is a very simple protocol. It can be made, there are many optimizations and so on, but there's a key idea here. Now, let's fast forward from late 20th century finance to today. So actually, maybe instead of today, maybe it's tomorrow. We'll see. So we're going to look at something called cross-chain swaps. So Alice has a beautiful pink Cadillac, which she wants to sell, and she wants to sell it for Bitcoin. Now, Bob, it turns out, has lots of Bitcoin and is dying to acquire a pink Cadillac. Now, this is the future, and the titles to cars are managed on the blockchain, and Bitcoin is, of course, managed on the blockchain, but they are different blockchains. So now, instead of coordinating changes on a database in New York and a database in Paris, we need to coordinate changes on an automobile blockchain and the Bitcoin blockchain. We now have a more formidable adversary, however. So instead of worrying about crashes, there are intelligent people out there who have lots of time, who are trying to do everything they can to pick your pocket, to steal your money. And the range of attacks that they have are wider and much more subtle than just crashes. There is, I won't go over each of these, but you have to be very, very careful. if you're going to operate in this, because the newspapers are full of stories of people who have been swindled out of large amounts of money. So the main thing that we're going to use is something called the smart contract. So first thing is, smart contract is a marketing term. A smart contract is not smart, and it's not a legal contract. A smart contract is really more like of a script. It's like a bash, a shell script. And what it does, it's used to escrow an asset. So escrow is a term from finance, which means that the contract takes custody of an asset. So the contract has temporary ownership of the asset, and it has authority to either give it back or it can give it to the other party. So if the conditions are met, then the contract will hand Alice's automobile to Bob and Bob's Bitcoin to Alice. If the conditions are not met, if something goes wrong, then the contract will refund the car to Alice and the coin to Bob. So the contract acts like a middle party. The contract is trusted because it's open source code, and the blockchain correctly executes the code. One thing I'll say is when I talk about is that the contracts I'm describing are probably most naturally expressed in a blockchain like Ethereum. They can be done on Bitcoin, but it's more challenging. Now, the key technical term that we're going to use, or the key technical device, is something called the hashlock. This is a very simple construct which we need to explain. So one party has a secret. Secret is just a large number chosen at random. And a hashlock is you take that secret and you hash it. Hashing it means you mix it up in a complicated way. And this has the property that if I know the hash of S, I cannot reconstruct S. If I have S, I can reconstruct each of S very easily, but I cannot go backwards. So what the escrow contract is going to say, the escrow contract has possession of the asset, and it knows the hash of the secret, but not the secret. And if you come to me and you give me the secret, that is, if you give the contract the secret, the contract will give you the asset. So the secret is, the contract can tell if you know the secret because it can hash the secret, and if the hash matches the value it had, it says, okay, you are correct. It's like knowing a password. But this is the only technical mechanism that we need. Oh, and one more thing. We need to have a timeout because it's possible that if you have a multi-step protocol, one party might crash, one party might walk away. So pretty much what the contract will say, if nothing happens in a certain amount of time, then I'm going to abort the transaction. I'm going to give everybody their assets back and just go home. So here we are. Alice has her automobile title, and Bob has his Bitcoin. There are two blockchains, one that controls the title, the legal document for the car, and one that controls the coin. And again, don't be, this could be any coin, not just a Bitcoin. And Alice invents a secret, which she doesn't tell anyone because it's a secret. And she creates a contract that says, transfer the car title to Bob if he produces a secret matching the public hash within 48 hours. Then Bob produces a contract that says, give my Bitcoin to Alice if she produces a secret that matches the hash within 24 hours. So in the first phase of the protocol, Alice gives over ownership of the car to the smart contract on the car title blockchain. When Bob sees that Alice has done this, and only afterwards, Bob places his own Bitcoin in escrow. So he hands ownership of the Bitcoin to the contract. Each contract can now decide who ends up, who finishes with each of the assets. When Alice sees that Bob has escrowed his contract, then Alice sends the secret to the Bitcoin contract. She says, here is the secret. You can verify that this is the correct secret. Give me the money. The contract verifies that the secret matches the hash and says, okay, here's your Bitcoin. A side effect of this is because everything that happens on the blockchain is public, Bob now learns the secret. Then Bob takes that secret and sends it to the car title blockchain. The car title contract says, yes, the secret matches the hash. The car is now yours. And there you go. You can see why the car title needs a longer timeout than the blockchain, or than the Bitcoin blockchain. Okay, at this point, everyone is happy because we have atomically exchanged the assets. You can check various things that can go wrong, and in fact, this assures that either the transfer happens or it doesn't happen. So this is, I think, Antonio talked about this in an earlier lecture. Now, what I want to emphasize is that this atomic cross-chain swap protocol is very similar to the two-phase commit protocol in many important ways. In phase one, in both cases, you secure the changes. In the database case, you write your changes to a disk so they don't get lost if there's a crash. In the swap case, you place your assets in an escrow where they are out of your reach. So you can't grab the escrow and run. In phase two, we check that everything is okay. And if everything is okay, then we complete the swap, or we commit both transactions. So this pattern of you secure the changes, if both changes are successful, then you complete the transaction. If either of the changes fails, or you don't get a response in time, then you roll back and abort the transaction. This is the common pattern in both of these. So if something is wrong, then you discard your changes and restore the original state. But of course, there are differences. And I think this example illustrates in some sense the difference between classical distributed computing and blockchain-related computing. For example, in the two-phase commit, it doesn't matter what order the databases save their changes. In the escrow protocol, or the atomic swap protocol, is very sensitive to the order. If you do things in the wrong order, the other party can steal your assets. So the order in which everyone takes steps matters. Timeouts have to be chosen carefully. I don't have time to explain what the rules are, but you have to be sure that one timeout is much longer than the other. There is no central coordinator. Each party does what it wants. If it conforms to the protocol, we guarantee that it completes and everyone is happy. If someone deviates from the protocol, we can guarantee that no honest party loses anything. And all of this is because the adversary is malicious and intelligent. You know, it isn't simply hardware failures. It's hackers sitting in a cafe somewhere watching your every move. So the next step is to go from swaps to options. So the idea here is let's revisit the steps in the protocol and see what happens when things go wrong. So here we are. We have both of our contracts set up, and I'm going to replay the protocol. So phase one escrow. Alice escrows her car. Now Bob is supposed to escrow his Bitcoin at this point, but instead he says, "Well, you know what? I have 48 hours to decide whether I want to complete this deal or to just let it be undone." So Alice's car cannot be stolen. Either the trade happens or Alice gets her car back, but that doesn't. But that's in some sense a naive measure of correctness, because now Bob just sort of sits there and he says, "Well, I have a long time to wait." And at some point he says, "I found a better deal. Goodbye. I'm leaving." And Alice gets her car back, but she's angry because her car is locked up for a long time. So she didn't gain anything, but she could have sold that car to someone else. She could have driven the car to see a restaurant, So Alice can't really win in this situation because Bob has complete power to decide whether to complete the swap at this point. Alice has given up her ability to affect things. If Bob decides, then it must be the case that Alice's profit improved or Bob's profit must have improved at Alice's expense. So if Bob is getting a better deal, then Alice is getting a worse deal. And so Bob can walk away if the deal turns against him. He can complete the deal if it goes on in his favor. So Bob is getting a very good deal at this point. If Bob chooses not to go through the deal, then Alice pays nothing and Alice's asset is locked up, which is a kind of an expense for Alice. So it's not enough simply to say, well, nobody can steal anyone else's assets. We also need to take into account what's called optionality, that the fact that Bob has power and Alice doesn't at this point. Now, in fact, we have rediscovered one of the oldest financial instruments. If you explain this problem to someone who does finance, they say, "Oh, that's called an option." So in an option, Bob pays a premium, a fee to Alice for the right, but not the obligation to complete the swap in the next 48 hours. So really what's going on here is before Bob had complete power, he could walk away without penalty. But if you set up such a deal on Wall Street, the person who's offering the option will say, "Okay, give me a 1% or 2% fee, so that at least if you walk away, then I have some compensation for having my assets locked up." So if Bob completes the deal, then Bob gets the car, Alice gets the coins, plus she gets a premium. If Bob says no, then Alice keeps her car, but she gets a premium. So this is a much more fair deal because it takes into account the value of the optionality, the value of the ability to make a decision is valuable. So some observation is if Alice's car is locked up but unclaimed, then Bob should pay her, say, Q coins. That's the fee for having the privilege of being able to decide whether to take Alice's car. If you look at the protocol carefully, there's also a window where Alice has optionality. So at the very end, Alice can decide whether to release the secret. And if Alice decides, no, the market has moved against me, I'm not going to release the secret, I'm going to just wait for the timeout and take my car back. The same kind of argument happens that says if Bob's Bitcoins are locked up but unclaimed for a long duration, then Alice should pay Bob. So and she should pay him P coins. So how can we change the protocol to do this? The premiums are computed according to well-known formulas for valuing options. Well, here's how we can do this. So Alice prepares two fees, one P and one Q. And Bob prepares one fee Q because the protocol, it turns out, is not symmetric. So in the very beginning, Bob puts his premium, his fee, in escrow. On Wall Street, a premium is usually about 1% of the value of the swap. And Alice puts P plus Q into escrow. Now, this may seem surprising since Alice is only supposed to pay P to Bob, but I'll show you why you need to do this. Then Alice puts her car title in escrow, and Bob walks away because he doesn't want to complete the deal. So Alice gets back her car. Alice gets Bob's premium because she locked up her title and Bob didn't claim it. Bob never locked up his Bitcoin, so Alice is refunded her premium. And so in the end, Alice gains a Q coins the way that, as we agreed. If we go the other way, if Alice decides to walk away, then both sides get their assets back. The car contract says, well, Alice's car was locked but unclaimed, so we pay Alice, even though it was Alice's fault. But the contract can't tell the difference. But the other contract says, well, Bob's Bitcoins were locked up but unclaimed, so let's refund Bob. And in this way, Bob gains P coins. So the point here is that designing protocols to support options, going from a swap to an actual option, is non-trivial. And doing this in more general cases requires some amount of work. But I think you can see that this is a kind of a form of nested two-phase commit. So this option swap, which we'll call the hedged swap, is like almost like two-phase commit with two phase ones. So this is phase one where we deposit the premiums. There's another phase one where we escrow the cars, and then in phase two we check that everything is okay and redeem it. So in essence, we made a small evolutionary leap from a swap that is unfair to each party because it doesn't account for optionality, to a slightly more complicated protocol that pays one party if the other party walks away. And again, what I want to emphasize is that this is very much similar to two-phase commit. It's more like 2 + 1 phase commit, but the ideas are roughly the same. So now, one problem you might say is, well, as soon as Alice deposits her premium, Bob could just walk away, and Alice will get her premium back. But we seem to have the same problem that we had before. But in fact, the premium is usually pretty small, 1% of principal. So maybe Alice doesn't care that much. So if you want to lock up an automobile for 48 hours, that's a lot. But if you want to lock up $10 for 48 hours, that's maybe that is tolerable. If it's not tolerable, then we can bootstrap. We can have multiple rounds of locking up. I can put in 10 cents, then $1, then $100, then the car, and you get basically the risks shrinks exponentially with each round that you deposit. Again, this is a very interesting subject, and if you want to read about it, we have a paper talking about how parties can protect themselves against other parties that walk away from a deal. Okay, so now I'm going to add one more ability to this option protocol. So I'm going to talk about transferable cross-chain options. And again, here we're moving into territory that looks like it's very far away from the simple 20th century database protocols. but I'm going to insist that it's still very much a similar idea, but well disguised. So here we are back in the middle of the protocol, and Bob says, well, here I have 48 hours to decide whether to take the car. Alice is happy because she says, my car is locked up, but I was paid a fair premium. So, I would prefer it if Bob completes the swap because I want those Bitcoins, but I will tolerate it if Bob walks away because I will be compensated for my trouble. Now, Bob decides, you know what? I don't want this car. I want to walk away, but I paid a premium. Maybe I could sell this option to someone else to help cover the cost. So maybe someone else would like the ability to complete this trade, even though I don't want it. And this is also something that, if you speak to people who do finance, this is everyday quotidian business for them. So you can buy an option, you can sell an option. There's a vigorous market in options. Reproducing this on cross-chain protocols, we'll see, is highly non-trivial, but it is something that it's a natural problem. So someone else comes along, say Carol, and tells Bob, I will buy your option rights. I have lots of Bitcoin. I really want a pink Cadillac. So I'm willing to take over your position. And so we could do this so that I'm going to show you a very naive protocol that doesn't work. So Carol can come along. Carol can escrow her Bitcoin. Carol, when Alice reveals her secret to claim the Bitcoin, then Carol says, I just learned the secret. She forwards the secret to the other blockchain and claims the car. And we've completed the protocol as before. And everyone would be happy. Now, there are several interesting reasons why this naive protocol I've described does not work. Some of you may have figured this out already. So for one thing, Bob still knows the secret, so Bob could go back and interfere. So even if Bob might be able to steal the car, or even if he can't steal the car, he might disrupt the protocol by releasing the secret prematurely. So one absolute requirement is that once Bob sells the option, he has no more power. And this is easy to state, but not so easy to do. So perhaps you could have a protocol where everyone agrees, let's replace secret S with another secret, S prime. So we have to replace the old secret with the new secret that Bob does not know. But it has to be one that Alice knows, because Alice needs to know that secret to claim the automobile. But Alice should not be able to prevent Bob from selling his option. So Bob should be able to sell his option whether or not Alice thinks this is a good idea. Bob does not want Alice to interfere. Carol does not want Alice to interfere. Since this is a blockchain world, we assume everyone is evil. And if they can't steal your money, they will at least disrupt the protocol. So we have to make sure that Alice cannot prevent the option from being sold. So Bob has to be powerless. Alice, after the sale, Alice should be not involved in the transfer. So in the end, we need multiple secrets and locks. It's a non-trivial protocol. And in fact, we're in the middle of writing a paper. We have protocols that do this, but what we're trying to do is to organize them in a way that's easy to explain. And it would take me another half hour to explain how the protocol works. But this is an example of what I think are interesting research problems in blockchain, because these are protocols that people want to do. If you look at the options market on Wall Street, it's billions of dollars. If you think that blockchains are going to take over the world, then they have to be able to support things like options markets that are already very popular in the paper world. So this is a kind of a necessary problem that needs to be solved if blockchains are to be successful. And I think there are many open questions. What's the right model? What's the right technology? What are the properties that you want? And these things have been extensively studied by people who study finance and economics, but not in the context of blockchains. So the economic theory behind options and transferable options is well understood, but the blockchain mechanics are still not well understood. So I'm going to wrap up, and I hope I have time to answer questions. So when we talked about two-phase commit, the adversary that we were worried about were hardware failures. And designing distributed protocols that tolerate hardware failures is difficult. There's also, timing model, synchronous, semi-synchronous, asynchronous. But hardware failures, in some sense, are limited. In the swap example, when Bob walks away and leaves Alice with her assets locked up, we were worried about a Byzantine predator. A Byzantine here simply means that the party, they can do anything they want. You can't trust them. They are treacherous and perfidious. And so we have, what we're worried about is betrayal by the other party. When we go from failed swap to options, instead of being betrayed, we say, okay, you might be able to walk away, but that is not betrayal. That is an option. This is the source of the title. Instead of being a failure, it's an option, a financial instrument. And as long as you pay me for the privilege, I don't care if you are an evil person. You give me the dollar, and I don't care. You can complete the deal. You can walk away. But at least I'm compensated for your betrayal. And of course, the technical challenges are that they exchange roles. At one point, Bob has optionality. Another point in the swap, Alice has optionality. If the deal falls apart, then you have to make sure that the protocol can figure out who is to blame and who has to pay whom. And this is non-trivial. But the idea that we change a form of failure, a form of betrayal into normal behavior that is paid for, is something that also shows up in the finance. When you rent an apartment, you leave a deposit with the landlord before you move in, so that you don't walk away. This is, again, one of the most common patterns in the real world, and it's surprisingly challenging to replicate that in the blockchain world. So what I like about this is this idea that a world where we only worry about hardware failures but we trust everyone looks very different from a world where we don't trust anybody, but we are concerned about more than one kind of cost and more than one kind of deviant behavior, to a world where we take the deviant behavior and we make it normal, simply by saying, if you want to misbehave, that's fine, just give me the money. These worldviews superficially look very different, but if you look at the mechanisms, we have two-phase commit protocol, this very simple protocol, making sure that everything is safe. Is it okay? Yes, okay, commit. The swap protocol, which is two-phase commit plus a little bit more carefulness and timeout because we are dealing with a more intelligent adversary. And then going from there to the option, to turning the swap into an option, where we explicitly recognize the ability to walk away. The mechanics are the same. Failed swap is kind of a nested two-phase commit protocol where we do phase one twice, once for the premium and once for the assets. Turning this into an option, we, in some sense, we're just compounding the same mechanism. So underneath, I claim that these jet fighters are still bicycles. Everything interesting that's happened since then are the ways in which they're different. But I think if you understand these kinds of blockchain instruments in terms of their origins, then it becomes much easier to understand what they're trying to accomplish and what they do, both in the ways they're similar and in the ways that they are they're different. So starting with two-phase commit, we looked at cross-chain swaps, very close to two-phase commit. We looked at cross-chain options, which is basically nested two-phase commit, in my opinion. You can argue with me. And then we made the options transferable, which is turns out to be deeply nested two-phase commit. But the same, we're building things out of the same atoms. So that concludes my talk, and I would love to answer questions. Thank you.
Thank you very much, Maurice. Thank you. And I don't know if there are questions. Let me check in the Q&A banner. Not at the moment, but if anyone has a question, maybe I will ask a question. Maybe someone else will follow. Just one quick question. Do you know if any of these algorithms or similar algorithms are used in practice nowadays, or this started more like theoretical research that
the atomic swap is used by several companies. The simple atomic swap. The options, I believe there's one. There's certainly been papers describing options. And I think there's at least one company that offers similar kinds of options. Transferable options, I think, are still subject of research.
I see.
But, there are also there's a lot of work that goes on to, for example, transfer assets from one blockchain to another. Where, for example, I can take a token on one blockchain, just burn it on that blockchain, mint a new copy of that token on a different blockchain. So these are called token bridges, and this is the big business. There are several major companies that do token bridges and similar kinds of things. So I think the answer is that some of this is currently done. The rest of it will be someday soon.
I see. And just I'm curious about the name premium. Yeah, this is the fee, no, that is paid. So yeah. This premium is fixed always, like this in this your example, this 48 hours is fixed, or it's possible to say if you do this transaction after 1 hour is this amount of money, if in 2 hours this amount of money, and so on until the 48 hours. So like kind of dynamic behavior.
You can certainly do dynamic behavior because the smart contracts have a reasonable notion of time, and they can tell they could do the computation. The actual computations are Black-Scholes and other kinds of fairly sophisticated mathematical formulas, which might be expensive to compute dynamically on a blockchain, but there are ways around that. So certainly you could do this dynamically. For simplicity, I presented it as if they were constant.
And I guess these interactions could include more than only two parties, like only like three guys trying to exchange different things in three different blockchains.
Yes. In fact, you could take any directed graph and set up a kind of a multi-way swap, and the complicated part is that if some things break down, then each contract has only a local view of the world. And in order to decide who is guilty, you need a global view. And this is why we need to do complicated things like transferring P plus Q instead of just P. So there are definitely ways to generalize all of this to multiple parties.
I see. Here I see that there is a question from Carlos Estrella. How open-minded financial institutions are about implementing blockchain solutions through smart contracts in order to enhance and optimize financial instruments like financial derivatives and letters of credit nowadays?
So this is changing rapidly. So today, there are companies like Coinbase and Voyager that are primarily blockchain-based that do billions with a B of dollars in business. More mainstream financial institutions are starting to adapt some of these. Now, the problem here is that a lot of decentralized finance is basically unregulated. And there is a lot of uncertainty and fraud and so on. It's very easy to lose your money in this space, and not from bad investments. It's because people will, do not always tell you the truth. So, but this is slowly changing. The regulators in Europe and North America are starting to impose rules. And though some people protest, I think this is a good idea because this means that institutional investors are starting to invest in cryptocurrencies. To me, what's valuable here is not a particular cryptocurrency; it's the service. If you want to do futures, derivatives, and so on the blockchain, there are a number of companies, including some that I work for, that are trying very hard to make this a reality. So I think that this is slowly becoming mainstream. There will be a lot of drama as regulators, clamp down on some of the wild excesses. But I would say in some number of years, this will be perfectly normal. Your pension funds will use these instruments.
I see. Are there more questions?
Armando, I have a couple of questions.
Yes, go ahead, please.
Yeah, they are from the registration form. So here they go. Jorge Alberto Cabrero asks, if a consensus is needed for each cryptocurrency transaction, and this takes time and computational effort, how is it possible that cryptocurrency exchanges can handle many transactions?
Awesome. That's a very good question. So my opinion is that some of these, like Bitcoin in particular, is extremely slow. And I don't think that particular technology is going to be very useful for commerce. Bitcoin is primarily like a speculative lottery ticket, and I think it's probably going to stay that way. Newer blockchains are much faster. So Bitcoin, if you buy something valuable, it takes an hour plus before you can receive delivery, before you can be sure that your transaction is on the blockchain. There are a number of blockchains that will do the same thing within seconds. So it's certainly the case that scalability remains a challenge, but the newer blockchains, which use other forms of consensus, not a proof of work, but things like proof of stake, are they use much less energy, they're much faster, they're frankly more secure. And so I think that the situation is changing, and the older blockchains like Bitcoin are not going to be able to keep up in the long term. But Bitcoin doesn't exist for things like stock trading. Bitcoin exists more as a gambling device than anything else.
Okay, thank you very much. The next question is almost in the same sense. It's from Laura Itzel Rodriguez. She's a student, a bachelor student at UNAM. How viable could voting in elections be using blockchain?
So I have reservations about using blockchains. I think there are many challenges. Blockchains are public by nature, whereas voting is, some parts of voting have to be private. So whether you voted can be public, but there are people who design electronic voting systems. It's important, for example, that you cannot reveal how you voted. So if someone wants to give me $1 million to vote one way, they're more likely to want to do that if I can prove to them how I voted. If they pay me $1 million to vote for Alice and I can still vote for Bob and no one can tell, then they're less motivated to try to pay me. So these are difficult problems. So I think it's eventually perhaps this will be useful, but I think there are very difficult challenges before blockchain systems can be used for voting.
Okay, thank you very much. There is another question, Armando, if you want to ask it.
Yes, there is one more in the Q&A banner. Yes.
Yep.
This one is from Hugo Rafael Ibarra Alarcón. While the digital properties like the ownership of the car is put in escrow, how are physical properties like the actual car handled? Are there employees that watch the car in the name of the blockchain organization? Does it work on the owner system?
That's a very good question. The many blockchain advocates tend to be libertarians. They don't like government, they don't like courts, they don't like police. But if you're going to sell your car, you need to have these legal instruments. So I'm assuming that the government recognizes the blockchain, the title on the blockchain. So if I sell you the title to my car and I drive the car around and don't give it to you, then eventually you'll report it to the police and they'll say, Maurice stole my car, here's the title. And they will stop me and take the car. So something on the blockchain that represents physical property like real estate, automobiles, even stock to some extent, requires a legal system to back it up. So, I'm not one of these people who say that blockchains are great because we can ignore government. I think that's a very naive and dangerous idea. Blockchains are great because when you combine it with, a well-organized society, then it can be very useful. So I would say the title to the car on the blockchain has the same power as the paper title that you would normally use when you sell a car.
And that's very interesting. But if I can say something, that is very interesting, but it requires an extra step, which is maybe even harder than the ones that we've been discussed, because that involves laws and the government, and that's pretty slow usually, right? So.
Oh, yes, but if you're selling a car, if you sell a car in some sense in the same way, we could meet somewhere. I give you the paper, and then I jump in the car and drive off very quickly. It's the same problem.
No, I mean in the sense that the government should recognize these digital blockchains and as something legal. I don't know how fast that could be, or when that will happen.
Oh yeah, this particular story happens in the future.
Yeah, I don't know when exactly, but hopefully it will happen.
No, I think that's probably not too far away.
Oh, I see.
Not next week, maybe not even next year, but 5 years maybe.
Okay, that's very interesting. Very nice. I think we ran out of time.